Here in the San Francisco Bay region is the location of a modern 1 million barrel aviation fuel depot. The depot consists of two groups of circular pre-stressed concrete tanks set at two levels to conform to the topography. Each of the tanks is 122 feet in diameter, 40 feet high, and has a capacity of 83,500 barrels. The tank consists of a 15-inch floor slab of reinforced concrete, a 10-inch circular pre-stressed reinforced concrete wall, and a 9-inch column-supported reinforced concrete roof slab. The interior of the tank is lined throughout with a continuous quarter-inch steel plate. For extra protection, the tanks are backfilled with 4 feet of earth. The location was chosen because of its access to water, land, and highway transport facilities. To prepare the site, 250,000 cubic yards of earth were moved. On each of these cleared areas, a tank will be constructed. Fine grading for the floor slab is completed by motorized grader. Mild steel reinforcing for the concrete floor slab is prefabricated and placed in a rectangular pattern. The reinforcement is supported on spacers so that it will remain in proper alignment when the concrete is placed. Above the reinforcing bars, steel angles are precisely positioned and welded into place. These angles are supported by steel legs. Concrete for the base slab is delivered to the site in ready-mix trucks and emptied into large wooden bins. From there, it is taken by clamshell bucket and placed directly over the previously laid reinforcement. In the peripheral areas, concrete is chuted directly from the ready-mix trucks. The concrete is vibrated to assure good consolidation. Using the previously installed steel angles to guide the screeds, the concrete is finished. To assure proper hydration, a commercial curing compound is sprayed over the surface of the concrete. About 600 cubic yards of concrete are placed continuously in one day to complete the 15-inch thick reinforced concrete floor slab. The steel lining plates for the floor slabs are delivered by truck to the site in sheets 8 feet wide and up to 40 feet long. These quarter-inch plates are placed by crane over the concrete floor slab, with the edges of the plates placed over the steel angles. Accurate positioning is completed by pinch bars. The edge of the plate is tack welded to the steel angle. Any unevenness is straightened by sledgehammer. Tack welding assures proper alignment necessary for the continuous butt weld, which is done by an automatic welding machine. . To assure absolute leak-proof construction necessary for aviation fuel storage, and to avoid contamination of the fuel, every inch of weld is tested. A soap lotion is applied to the weld and a vacuum box placed over it. If a leak were present, it would show up as soap bubbles in the box. The entire floor slab, requiring 70 tons of steel plate, is lined and tested in 4 days. Here we see 7 tanks in various stages of construction, while in the foreground, the fine grading for the remaining tanks is in progress. To support the roof slab, 40-foot-high columns are erected. Each has a base plate, top plate, and 2 horizontal bracing struts. These bracing struts, made up of back-to-back angles, are bolted onto the columns at the site before they are raised to vertical position. The free ends of the struts are then bolted onto the columns already erected. Diagonal bracings complete the stiffening system. The base of each column is positioned and welded securely into place. To the top of the columns, beams are attached which will later support the roof. The 69 columns required for each tank are erected in 4 days. Moving on to the construction of the steel lining for the walls, quarter-inch curved steel plates previously bent to radius in the fabricating shop are hauled to the job. The plates are lifted into position by crane. Each plate is 40 feet long and 8 feet high. Once in position, the curved plates are held in accurate alignment by wedges preparatory to welding. Installation of the steel plate is aided by men on the inside of the tank, where circumferential working platforms have also been erected. Before welding, temporary stiffening beams are installed to ensure sufficient rigidity of the quarter-inch plate. The vertical seams between the plates are also wedged into alignment. A continuous hand weld joins the edges of the steel plates, the weld being built up from both the inside and the outside. The men work from circumferential scaffolds. A rolling scaffold suspended from above is another technique for reaching the work areas on the outside of the tank. Studs are fusion welded to the steel lining. These studs will secure a firm anchorage between the steel lining and the concrete to be placed against it. At the bottom of the wall, as well as the top, heavier studs are used. Here, the wall plate is welded to the circumferential steel angle. Testing is applied to all wells. Here, the bottom seam is tested with penetrating oil. The wall wells are tested from the inside by the vacuum box method. Where the wall lining joins the roof, again a steel angle is welded around the edge. The 80 tons of wall steel plate required for each tank are erected in 12 days. A grid of roof beams will support the quarter-inch steel roof lining. Special closure pieces to fit the curvature of the tank were pre-cut to the required shapes. Again, before welding, the plates are tack welded and the edges straightened, with the edges of the plates overlapping. A continuous lap weld by automatic equipment joins the plates. The weld around the edge of the roof is done manually. "70 tons of roof plate are installed in 5 days. With the roof plates installed, work on the walls can now proceed. Before placing the concrete core wall around the steel lining, vertical reinforcing bars are suspended from the roof of the tank and tied securely. These wooden forms for the concrete core wall are sprayed with bond-breaking compound to allow easy stripping. 24 of these forms, each 16 feet long, are required to form an 8-foot-high section of concrete around the tank. The concrete is placed between the steel plate and the wooden forms, which are anchored by ties to the lining. As each 8-foot ring of concrete is completed, circumferential bars for the next section are fastened to the vertical reinforcement. After the concrete has set, the forms are moved up to the next level. The 5 rings, requiring 450 cubic yards of concrete, are placed in 5 days, completing the core wall. The reinforcing steel for the concrete roof slab is laid and tied in a rectangular pattern. Concrete is lifted by crane to the roof and placed directly from the bucket. Another crane supplies a hopper on the roof, from which buggies distribute the concrete to the center area. The surface of the concrete is leveled by float finishing. The The entire 9-inch reinforced concrete roof slab, consisting of 350 cubic yards of concrete, is placed and completed in one day. Here we see the 12 tanks in various stages of completion, with some of the tanks ready for pre-stressing. In the pre-stressing operation, a preload wire winding machine applies spring steel wire under uniform tension continuously around the concrete core wall. This pre-stressing gives the tank the necessary strength to withstand internal liquid loadings and vapor pressure. It also increases its capability to withstand external loads. The spring steel wire is delivered to the site in paper-wrapped coils and stored on wooden skids. The starting end of each coil is threaded through a die. The coil is lifted to the wire winding platform and placed on its reel. The new coil is now spliced to the end of the wire previously wound. The final wraps of the preceding coil are clamped together to maintain tension. The start of the new wire, with its die in place, is threaded through the die holder. Here seen positioned below the platform. The ends are connected by a torpedo splice. Slack is taken up and the wire winding operation is resumed. The die post holder is now in its usual position above the platform. In the preload winding operation, the stressing of the wire is achieved by drawing it through the die. The wire is laid in its proper position on the core wall under accurate initial stress of 150,000 pounds per square inch. The machine is self-propelled and operates at speeds up to 8 miles an hour through sprockets which engage an endless chain around the tank. The wire winding deck is suspended from an overhead carriage encircling the edge of the roof. The carriage is anchored by cables to a center pin. The wire is applied in 4 layers at the bottom, tapering off to a single layer at the top to conform to the design loads. The machine can install 10,000 pounds of wire in an 8-hour day. Each tank requires 56,000 pounds. Mortar is used to protect each layer of wire. The mortar consists of 1 part cement and 3.5 parts sand. The wall is wetted down and the mortar is applied pneumatically. The men work from scaffolds mounted on a truck which circles the tank. Each layer of pre-stressing wire is flash-coated with this cement mortar before the subsequent wire layer is wound. Throughout the operation, the tension of the wound wire is carefully checked. A final cover coat of mortar is applied over the last layer of wire. Finally, a bitumastic sealer coat is applied before earth is replaced around the tanks. The entire pre-stressing operation, including the application of the cover coat, took 13 working days for each tank. Here, after 8 months of construction, is an aviation fuel depot of great strength and reliability. Designed for underground use and capable of resisting blasts of atomic force. 12 pre-stressed, steel-lined concrete tanks, absolutely leak-proof, with a combined capacity of 1 million barrels. Pre-stressing made possible the construction of these 40-foot-high tanks. This preload method was responsible for these tanks being selected by the owner as meeting the rigid criteria set forth for the installation in guide designs issued by the Military Petroleum Supply Agency, which is leasing the facility. This important project was accomplished efficiently and economically through the unique process of pre-stressing.